Good morning and welcome back to the modules on acoustic phonetics. This is module 15, Acoustics of Non-Resonant Consonantal Speech Sounds. In the previous module, we had a close look at the vowel sounds, and these vowel sounds were defined as resonance, plus vocalic, plus syllabic and plus sonorant sounds, also minus consonantal. Now coming to the consonants, in articulatory terms, if you recall, you must have defined consonants as obstruents, the speech sounds which are articulated with some obstruction in the mid-sagittal section of the oral chamber. So some of these sounds have been described as, consonants are described as obstruents, plus obstruents. If there is no obstruction, then they are vowel sounds. This is the conventional kind of definition. Now, no obstruction also means that the air column is free, the air passage is free without any obstruction. Therefore, resonances can happen, and therefore, plus resonant, plus vocalic, plus syllabic, plus sonorant, all of these features come into the picture, and we have defined our vowels in that sense. So, consonants in similar terms could be defined as plus obstruents and plus consonantal, but minus resonant, minus vocalic, minus syllabic and minus resonant. They are more in relative terms. We shall see some of the consonants can be syllabic too, and some consonants can show resonances too. Resonance is an important parameter as far as acoustic phonetics is concerned. In articulatory terms, the first parameter was obstruction or no obstruction in the oral chamber. But resonance as a parameter, we find the presence or absence of resonance in the oral chamber is an important parameter, acoustic parameter for distinguishing between consonants and vowels. So, plus resonance plus sonority gives the auditory experience of musical, whether this is musical or not, as compared to, in relative terms, minus resonance, minus sonority will lead to the auditory experience of non-musical sounds or perhaps noises. You can call them noises. So, music versus noise is another parameter. This is the auditory experience, but it has actually been used to make a distinction between the two classes of speech sounds, consonants and vowels. Look at Mamberg, 1963. He says it's possible to establish a division of the sound material of language into musical and non-musical. Musical would mean periodic and periodic vibrations, noises, or non-musical would mean aperiodic or non-periodic vibrations. And this division, he says, roughly corresponds to the traditional division of vowels and consonants. Further, he says, now consonants may be pure noises. Now, what is this pure noise? Pure noises meaning without any participation of periodic vibrations. Voiceless consonants fall in that category. But noises, the other consonants can be noises combined with a laryngeal tone, which is a kind of, periodic vibration. So, voiced consonants, b, v, z, etc. will be the other kind. So, but they are still referred to as noises. Look at the two figures given below. The first one, top one, is considered musical. It has a very clear periodic vibration, and the lower one is noise, hardly any regular pattern. Now, the consonants, as I mentioned, some consonants can have an acoustic structure like that of vowels. Let me go back to this figure where we are saying plus consonantal can be consonants as well as glides. So, certain other sounds, consonants and liquids, and minus vocalic sounds can be consonants and liquids. So, there can be, apart from consonants, there can be consonants which have vowel-like qualities or music-like qualities. Look at m, n and l for instance. M, n and l, they have something similar to the vowel sounds. Like you can see some formants. These three pictures are given where there are two vowels and in between you have a m or a n or a l. This is intervocalic position for the three consonants. They can show some resonances and they can show some, higher sonority, and in some contexts they can also become syllabic, like button and mutton and bottle. All of these are examples from English or syllabic consonants. Look at fricatives now. The fricatives are high frequency, high intensity noises. Obviously, there is no formant pattern, there is no proper organization of the acoustic field as as F1, F2, F3 proper resonances, nothing. So the spectrograms of fricatives, there are some spectrograms produced here, and you can see it is high frequency range within which you see high intensity noise. Particularly has the highest frequency, may be considered sharp, where 8000 to 9000 hertz is the range, or coming down to, or even if starting at 6000, it goes right up to 8 to 9000. Were in the range of 6000 to 7000 hertz. Less sharp but still not grave. But look at her, mostly grave with concentration of acoustic energy in relatively lower frequency range. So there is noise but in the lower frequency range. So fricatives can be of different qualities, and sharp versus grave is the auditory quality that we associate with those. And just put it on the vowel triangle, E as the frontmost vowel, front high vowel, U as the back vowel, and A as the open back vowel. And in comparison, we find S as sharp, as like E, and in the U position we find F, Sh, V as less sharp, and H, H, G are the fricatives which are definitely on the grave side rather than sharp. Now talking about stop consonants as pure noises. These voiceless stop consonants, p, t, k, they are pure noises. B, d, g and all of those are noise plus laryngeal tone. So they are the voiced stop consonants. Now how do we make a distinction between p, t and k as distinct stop consonants with different places of articulation? We find plosion in the highest frequency range for t, alveolar or dental, or sometimes retroflex as well. So the highest frequency range, there is a plosion or a noise in the highest frequency range. They are velars, dentals and alveolars. Plosion in the high frequency, or let's say middle range, not as high as the middle range, are the frequency range is k, which is less sharp than t. Plosion in the lowest frequency range, we find they are bilabials and they are considered grave. Once again, a comparison with the vowel chart, sharp and grave. You can see t in comparison with E as the sharp sound, and k as less grave, and in that triangle, p at the bottom. Now, based on sonority, now we bring in vowels again, because the entire range of speech sounds has also been arranged as cited in Mamberg. Jespersen gave this sonority chart long back. The voiceless stop consonants at the top in terms of the lower level of sonority. And as you go down this chart, you will find A as the most open vowel has the highest sonority. So low to high sonority, all the entire range of consonants and vowels fits in between this range. Now consonants in continuous speech, that's a very big challenge. what you have on the screen is the spectrogram of a sentence below, and this is a spectrogram taken many years ago by a conventional kind of an old model spectrograph, not computer-aided spectrograph of today. So, or computer softwares, which give you spectrograms today. So, this was the old model where a narrowband spectrogram is given to you. Pani Parkelia is the Punjabi sentence which is articulated here, and you can see the concentration of acoustic energy in these very clearly marked bright columns which are mostly vowels, and in between you have consonants, particularly stop consonants can be seen as huge gaps between these columns of vowels. So, vowel formants are resonants, vocalic sounds which are kind of carriers of all speech sounds, and they also make syllable peaks, and they carry the preceding or the following consonants. In the last module, we had shown how vowel formants change in continuous speech. If it's a vowel A continuing for a long period of time, it will still be steady state. Any vowel, steady state formants. But if two vowels in a sequence come, then steady change formants can be seen. Vowels with glides, gradual change formants can be seen. But look at the last part of this figure, consonant plus vowel, meaning the consonant which is preceding the vowel formants, that is causing a change in the vowel formants. So, you understand the consonants better when you look at the acoustic properties of or acoustic features of the following vowel sound. Now, that is an important, the abrupt change formants with that formant pointing downwards, meaning starting at a lower energy level and going to a higher frequency level. So, that is the influence of the plosion of a previous consonant. So, acoustic cues for the identification of consonants were naturally a very big challenge for one of the main reasons that the cues of consonants, to identify consonants in acoustic terms, you actually had to look at the vowel formants. So, the adjoining segment, the segment that follows the consonant, carries all the information about the consonant. So, therefore, it's important that we revisit our notions of segments in a continuous chain. We actually have syllables in a continuous chain. A syllable which has vowel as its peak carries all the properties of the preceding following consonants as well. So, and the history of this part of research is not very old. I think it was in the 60s, not very old history, not very long back in the history. 60s in the previous century, we find there were lots of experiments conducted at Bell Laboratories, Huskins Labs, using pattern playback and spectrograms. Spectrography was there, but pattern playback as a tool came in handy once they started using this in the Huskins Labs. So, a series of experiments called analysis by synthesis technique followed, which means you look at a spectrogram, you make a hypothesis that probably this speck on the spectrogram is an indication of plosion burst or fricative noise or something, So, you use that and put it on the, mark or make a similar drawing on a plain piece of paper and feed this into pattern playback. See if it sounds the same. So, a number of experiments were done on pattern playback. These are the series of experiments called analysis by synthesis technique. So, these were speech synthesis programs which were developed, and hand-painted spectrograms of vowels and consonants and vowels put together were analyzed. Some of these are very important research papers which gave us a lot of information about consonants and acoustic properties of consonants. 3 major acoustic cues which were identified for the identification of consonants. 3 acoustic cues were noise burst. So, if we have plosion, there should be something like noise burst frequency. Where on what frequency scale, where on frequency scale this noise burst is placed, that was important. Then formant transitions, how the vowel formants change, and acoustic locus or acoustic loci were the 3 important acoustic cues which emerged after these experiments. Talking about noise burst frequency, let me remind you of these formants which we discussed. These are the vowel formants. If you have 8 peripheral vowels, and these are the relative positions of the formants in comparison with each other. So, if these are the formants, now suppose you were to place a noise burst along a frequency scale to see what kind of auditory effect that has, what kind of a consonantal sound it gives you before preceding the vowel sound. So, what you do is you imagine 10 or 12 such bursts of noise along the frequency scale, starting at 200 Hertz and going right up to 3000 Hertz. And you place them, let's say if you have 10 such bursts of noise and these 8 vowels, or 12 such noise bursts, specks of marked as specks on a hand painted spectrogram, and you can use something like this. You can have like vowel E, 2 formants are placed far apart, and there is a noise burst you can see somewhere placed in the middle zone or a lower zone. Then vowel R, 2 formants are together, vowel U, 2 formants are together and lower. So, these 3 kinds of formants are with a burst of noise placed on the same frequency with these 3 formant patterns. The other picture shows that you have 2 formants of the same vowel, let's say A, but the 3 noise bursts are placed along different levels on the frequency scale, one in the higher zone, the other in the middle zone, and then in the lower zone. So, these individual units are fed into pattern playback and then received by the hearers to say what they hear. The results were fantastic. They are amazing results. Just take a look at the results, summary of the results. What you find is, if there is a noise burst, a speck of noise placed along the formants, if it is somewhere close to formant F1 or F2, then what you hear is most often K sound. It could be ki or K or Ka or Ka or Ko or Ku, whatever. If it is in the lower range but not too close to the formants, then it is always heard as P. Lower, or let's say the middle range also, it is often heard as P if it is not too close to the formants. And if it is placed in the higher zone, higher frequency range, then it's always heard as a T or a T, the dental, alveolar or a retroflex stop consonant. So, which means the acoustic cue for the frontmost stop consonant P and the backmost stop consonant K, velar consonant K, they are quite mixed up. Similarly, K and T can be mixed up. So, if there is channel noise and if you are talking on phone and there is some noise, you can hear Pa as Ka or Po as Ko, because the noise burst may be placed somewhere in the vicinity of the formants, and it may be, it is too close. So, but as far as E and A is concerned, probably that kind of confusion may not exist. So this brought in a lot of new information into our understanding of segments as independent autonomous units. Now these segments do not appear to be independent autonomous units. They are actually together, the two segments, the sounds coming with vowels, they are seen together, and a number of acoustic cues are seen in the vowel formants. So then the next point was the formant transitions in consonant-vowel sequences. Again, using the same kind of formant patterns, the formants are placed like for E vowel or A or A, they move from the extreme positions to closer positions and go to the lower part of the segment, meaning following this particular pattern as that you see on the screen. And then what you find is that the transition gives you lots of cues about what kind of a consonant is preceding the vowel sound. If the formant is pointing downwards, the second formant pointing downwards, it is often bilabial. And if it is sometimes pointing upwards, meaning starting at a higher frequency coming down to lower, then it is a dental or an alveolar sound. And if it is still pointing upwards but much higher, pointing much higher, see the summary of the results. What you find here is a velar sound where the F2 is pointing much higher. So, and the F1 formant transition shows practically no transition if it is a voiceless sound, but there is a transition in the F1 with a little noise bar, or call it voice bar, for a voiced ba, da, ga, consonant. For a nasal, you see nasal formants as well, and perhaps voicing too. And F2 transition is the same. For a velar sound, it has to come from a much higher position to lower. Now, the experiments conducted were actually Lieberman, Delattre and others, tempo of frequency change as a cue for distinguishing classes of speech sounds. Tempo of frequency change. This formant transition shows that the formant frequency is changing from higher to lower or lower to higher, and that tempo of frequency change gives you cues to distinguishing different types of speech sounds. The third feature is locus hypothesis, and this particular figure actually diagrammatically, schematically shows how a certain energy locus can be imagined. You can imagine a locus for a certain type of consonant along the frequency scale, and that varies for different consonants. Now, this particular diagram shows that the F1 is constant for all of them, and F2 varies from something very close to the F1, and the others are as you move the formants higher and higher and higher. All of them are put together, and what you see is you hear b, the, gs with different locus, different kinds of loci, meaning the formant transition is actually pointing towards energy locus, some energy locus for a particular consonant, another energy locus for the other consonant. So perhaps for bs or bilabials, the energy locus may be in the lower range. That's why the formants are pointing lower, downwards, and for ts and k's, it may be in the higher frequency range, and therefore formants are pointing upwards. So these experiments are also, in fact, let me mention these three references particularly. Cooper, Delattre, Lieberman, Bost and Guestman, these 4 or 5 people as a team, they published these articles, And Cooper et al. 1952, some experiments on the perception of synthetic speech sounds. This is where they identified, these three basic, burst of noise and formant transition and locus. Delattre, Lieberman and Cooper, same team, but Delattre, the first author, 1955, he talks about acoustic loci and transitional cues for consonants. And then Lieberman, Delattre, Gerstmann, Cooper, tempo of frequency change. So again, formant transition as a cue for distinguishing classes of speech sound. These kinds of experiments in the 60s actually changed our perception of the acoustics of consonants and the acoustics of consonants and vowels in a sequence. So the unit for analysis, the existence of multiple cues for the identification or perception of an acoustic unit, C and V together, is only one of the examples of how experimental evidence has changed our views of segments, discrete speech segments versus segments in a sequence. A sequence of discrete speech sounds is transformed into a continuum such that one perception of a sound depends not on one segment which may be taken out of that and analyzed acoustically. No, it is the analysis along different points in time along the sound wave which can help you understand the sounds in a sequence much better. So, there is a lot more on the study of vowels and consonants in acoustic terms, but these two modules basically give you the elementary information about what is happening, how do we understand vowels and consonants acoustically. And this is what leads us to various kinds of, softwares and programs you can explore further and read up further. And, with this basic information, it will help you understand all the other articles which are published from time to time on consonants and vowels and their acoustic properties. Thank you very much.